Good morning, guys. Welcome to the last new lesson of the year. Now, next week there will be a couple of videos posted, but what you're going to be doing is just looking back at the 4 tests that you've taken this quarter and doing a little analysis of those. So there will be some videos with those, but they will not be new lessons. Okay, so I don't think I mentioned it, but you need to, if you can get your hands on this, the chapter 11 tip chart. There is this bottom box that we didn't talk about in chapter 11, and I want to come back and talk about it now because today we are doing this lesson 11.7, and I know that seems a little bit weird to do lesson 10.4 yesterday and lesson 11.7 today, but you will see why I think they go together when we get to it. Okay, so there's the term on the bottom of the chapter 11 tip chart is similar solids, and remember, solids are all of the polyhedra plus like spheres, because you know a sphere isn't in the set of polyhedra because there are no polygons around around the side. So remember, a polyhedron is a 3D figure made up of polygons, but we want to include spheres in there. Okay, so similar solids are 3-dimensional shapes in which all corresponding dimensions I'll talk about that in just a minute, are proportional. Now, it's been a little while since we talked about similarity and what it means to be proportional, but remember, proportional means equal ratios. In other words, the scale factors are equal for all of the dimensions. Okay, so when you're talking about the whole big group of solids, different solids have dimensions that you would have to look at. So like sphere, all you would have to do is compare a radius, because a radius is the only dimension that a sphere needs to form, right? Well, cylinders, they need a radius of the circle and they need a height of the cylinder. And cubes, they need a length and a width and a height. Actually, that would all be the same dimension. So all cubes would be similar. But rectangular prisms like this one, all right, they 2 rectangular prisms could be similar or they might not be similar. So let me show you what I mean by that with some cans that I got in the pantry. Okay, so here's 2 cans. These are 3-dimensional figures, they're cylinders. These are not similar because this one here is a tall skinny can, right? And this one here is a short squatty can. So they're both cylinders, but they're not similar cylinders. If you did the ratio of the radii, it is not going to equal the ratio of the heights. So so they're not similar. But these 2 cans, they're almost similar. I did this one, the radius to the height, and it was 5 to 8. And then I did this one, the radius to the height, and it was 6 to 8. These were the closest I could find without measuring every single can in my pantry. So, so these are pretty close to being, see, you can tell that they're almost like the same shape. Almost. This one needs to be a little bit bigger radius. Okay, so that's what it means to be similar when you're talking 3-dimensional. All the corresponding dimensions have to be proportional. So see how this radius is 2 to 6, which reduces to 1 to 3, and the height is 1 to 3. So these would be similar solids. Okay, so in this lesson, just like yesterday's lesson with area, yesterday we were talking about area and perimeter of similar flat shapes, 2-dimensional shapes. Today we're talking about perimeter, surface area, and volume, mostly surface area and volume of 3-dimensional similar shapes. So, so that's what this lesson's about, and that's why I think they go together. All right, so, and by the way, about these last 2 lessons, these lessons won't be on a test for you in this class, but SAT writers, test writers, they like similarity questions. They like similarity questions with triangles, you know, flat two-dimensional shapes. They like comparing the areas of similar flat shapes. They like comparing the volumes of similar three-dimensional shapes. So that's why, I mean, I could have just ended since these 2 lessons aren't on a test, but I just didn't want you to sit down to your SAT and happen to see these kind of questions on it and not know what to do. All right, so see this big old chart? This is the chart that we made yesterday in lesson 10.4. So see, I made like a 3-column chart for the questions. And one was for the scale factor, one was for perimeters, and remember I told you those are the same, so you really technically could have just 2 columns, this one and this one. And so this is lesson 10.4. This is lesson 11.7, sorry. But with these 2, I would put scale factor. Okay, I'll show you what I mean by that in just a minute. But it's another section where I draw a little chart. All right, so question number 1. First of all, before we get to the chart ones, it says, are these solids similar? So going back to the definition we just wrote down, to be similar, all of the corresponding dimensions have to be proportional. So you write ratios of the corresponding dimensions. So you go height is to height. Hold on, my forehead got a little skinny there. And I just happened to pick up a smudgy pencil, sorry about that. And then you do side length to side length, so 2 to 3. 2 to 3, and the question is, are they equal? Well, 4 to 10 reduces to 2/5. 2 to 3 is already reduced. My numbers, y'all. Ugh. 2 to 3. They are not equal. So you can kind of tell by the picture, but you shouldn't, you really shouldn't just look at it and go, oh, they're not similar, because, they're not always drawn to scale. But you can kind of tell that they weren't the same shape of pyramid. This one's taller. So yeah, you can tell by their ratios, since the dimensions are not proportional, those are not similar solids. So the answer is a big old no. All right, the next example, it says the surface areas of 2 similar solids. So they're telling us that they're similar. Notice that we don't even know what kind of solids they are. We don't know if these are cylinders or if these are spheres or pyramids. It does not matter. We just know that they're 3-dimensional. And they're giving us surface areas. And then it says the volume of the larger one is 4,860. What's the volume of the smaller one? So yesterday when I was talking about similar 2-dimensional shapes, I made a little chart, and I'm going to make a little chart for 3-dimensional shapes. Okay, if you want to, you can put them all in one chart. So look, this is scale factor and perimeter, because remember they're the same. This one is area and surface area, and this one is volume. Now, this is both lessons together. So if I make a chart like that, this is 10.4 and 11.7 together, because 10.4 talked about scale factor, perimeter, and area, and 11.7 talks about scale factor, surface area, and volume. So this one, scale factor, and these 2. So, I mean, you could do it like that, or you could, I've seen some people do this. Whenever they're talking about 3-dimensional, they put scale factor, surface area, and volume like that, because those are the ones for 3 dimensions. All right, if you look at them together, this perimeter and this area would be of the sides of the 3-dimensional shape. It would be of the flat figures. All right, so it says the surface area of 2 similar solids are these. 192 over 1728. That's the ratio of the surface areas. And I put it there because because it says that, are those 2. Okay, now, I would reduce that. It very likely reduces, and I know it does because they're both even, but I would reduce it. If you don't want to take a lot of time reducing, you just type it in a calculator with the ABC key, and the calculator reduces it for you. 192 over 1728, you get 1/9. So that reduces to 1/9. Now, I did not do anything to that other than reduce it. So 1/9 is the same exact thing as 192 over 1728. So same thing. All right, so that's how their surface areas are related. So the surface area of one of the solids is 9 times as big as the surface area of the other one, of the smaller one. Okay, now I need to finish this chart. Okay, so if they give you this middle one, remember yesterday whenever they gave us area, it was squared already? I might have written already squared, but anyway, this ratio is squared. So if we want scale factor, we have to unsquare it. So square root. All right, so if the areas are related 1 to 9, the scale factor is related square root of 1, which is 1, over square root of 9, which is 3. So the scale factor is 1 to 3. And then I can get the volume ratio. Now, you can't go from area ratio to volume ratio. You have to know the scale factor to get the volume ratio. So let me show you up here what I mean. The volume ratio is A cubed to B cubed. So you have to know what A and B are. You have to know the scale factor. So that's why I unsquared the area ratio to get the scale factor, all for the purpose of getting this volume ratio. Okay, so the volume ratio is this one cubed. So 1 cubed is 1 times 1 times 1. And 3 cubed is 3 times 3 times 3, which is 27. So here are your 3 ratios, 1/3, 1/9, and 1/27. There are some questions in the homework that will just ask you for these ratios instead of asking you for a volume. So some of your homework that you're done in this chart. All right, so now we can answer this question. It says the volume of the larger of the solids is 4860. Well, here's how their volumes are related. Their volumes are related 1 to 27. And the larger one is 4860. So see how when we wrote 1 to 27, that's smaller, that's larger. So the 4860 has to go on the bottom. And the volume of the smaller one is on the top. So see, this chart tells you how the sides are related, the dimensions, how the areas are related, in this case surface area because it's 3-dimensional, and how the volumes are related. So we used the volume ratio to do a volume problem. All right, so then when we cross multiply, we get 27x equals 4860. And then you divide by 27. Now, I think, just personal opinion, I think this process is kind of complicated. So it takes a little bit of time and thinking, so try not to rush through these problems. 180 meters cubed. So when I solved that, I got 180 meters cubed. All right, number 3. Another type of problem is one where they're not asking you to do a proportion, they're asking you for a scale factor and a ratio. So whenever they ask you for a scale factor or ratio, your answer is going to be in this chart. You don't have to then go and use it in a proportion. Okay, so it says the volume of 2 similar solids. So I'm going to make this chart. And just personally, I like to put both sections all together. So I like to put scale factor and perimeter in one, area and surface area in the other, and volume in the last one. All right, it says the volumes of 2 similar solids. They're giving us this one, 343 over 1331. I need a bigger column because I'm about to reduce that thing. So, see, sometimes you may not want to spend time reducing that, although these numbers give you a little hint about what it is. So anyway, 343 ABC 1331. Ooh, that did not reduce. Let me make sure I'm right. 343 ABC 1331. Yeah, it doesn't reduce. Okay, so I guess I didn't need a bigger chart. Okay. Oh, I know why. I just thought of this. All right, anyway, so these are the volumes. They want the scale factor. So we're gonna go from volume to scale factor. So remember up here I told you that when I had 1/9, I couldn't do anything to the 1/9 to get the volume. I had to go from scale factor to volume. So I just remembered why this didn't reduce. I'm going from volume to scale factor, okay, from volume to scale factor. Well, if they gave you volume, this one is cubed already. So see, if they give you areas, it's squared already. If they give you volume, it's cubed already. And I'm gonna go from volume to scale factor because you can't go from volume to areas. This one's cubed, this one's squared. Okay, so we're gonna take our fraction 343 over 1331 and we're gonna take the cubed root of it. Now, you can take the cubed root of the whole fraction at one time, but sometimes I'm afraid I'll forget to put parentheses in the right place. So I'm gonna do the cubed root of 343. Now we did this a little bit in the sphere section. So here, let me remind you how to do cube root. You press 3, you press second, and you press this caret. And that means cubed root. It looks like it says 3 times x root, but the calculator, the algorithm, what it's programmed to do is put the 3 right in there. So that's a cube root. And we're taking the cube root of 343. That is 7. Now, when I uncubed, I'm going all the way to the regular single number. It's not squared. And then I'm going to do the same thing with 1331. So press 3 for a cube root, press second and caret. That takes the cube root, and then put 1331. And you get 11. So 7/11. So that's why that thing didn't reduce. It's because these are perfect cubes. All right, so now that we've got scale factor, we can find the ratio of the areas. We just take the scale factor and square that. So square this. 7 squared is 49, and 11 squared is 121. So, okay, that's the question they asked us. Find the scale factor. We got that, 7/11. And we have the ratio of the surface areas. That's this middle one. So the answers are those two ratios, 7/11 and 49 over 121. Now, some people, once you get these numbers, some people think, oh, I'll try to reduce that. But remember, that came from squaring. So there's a 7 and a 7 in there. And that came from squaring. So there's an 11 and an 11 in there. So this won't reduce either because they have nothing in common. All right, so just be careful about whether the question is asking you for ratios or whether the question is asking you to use a ratio. Okay, so if they ask you for ratios, which is a scale factor is a ratio too. So scale factor, ratio of the areas, your answer is in this chart. It's just the fractions in the chart. If they give you one surface area and ask you for another, or if they give you one volume and ask you for another volume, you're still going to use the chart, but then you're going to write a proportion with it to answer the question. Okay? So that part is sometimes tricky for people, is whether to use it in a proportion or not. All right, so that is all to similarity with 2-dimensional figures and 3-dimensional figures. And that is all. So we're done learning new lessons in geometry. And this was such a weird way to do it, but I'm so happy we got to continue and you guys got to finish, and you have you've seen all the things you'll need to see that might be on the SAT from the subject of geometry. So I'm happy about that. And then next week, all you'll have to do is look back at some previous tests and just do a little analysis of those. So that's it. Y'all have a wonderful day. Bye.